Welcome back. During this lecture, I'm going to talk about model-free reinforcement learning techniques, which range from Monte Carlo to temporal difference. I will talk about Q-learning and deep Q-learning, and I will explain these techniques with practical examples and Python programming. Reinforcement learning techniques divide to model-free and model-based techniques. I want to focus on model-free techniques because to find optimal policy without having the dynamic of the system, we should use model-free techniques, I mean Q-learning, to find the optimal policy. About model-free reinforcement learning techniques, I want to talk about some prerequisites about reinforcement learning. At first, I'm going to talk about Markov Decision Process, which provides a mathematical framework for solving the reinforcement learning problems. There are two main concepts about Markov Decision Process, Markov property and Markov process. Markov property means that the future just depends on the present and it doesn't depend on the past, which is a simplifying assumption, but it can reduce the accuracy. Markov process just consists of a sequence of states that obey the Markov property. And for example, if we want to predict the weather for tomorrow and the day after tomorrow, there are three states: being cloudy, being rainy, and being windy. The transition probabilities between these states for these days are shown in a transition matrix. The Reward process is an extension of the Markov process. In Markov process, we had states and transition probabilities, but in Markov reward process, we have those components that we have in Markov process plus a reward function. But in Markov decision process, which is an extension of MRP, and we have those components with actions. I mean that there are states, transition probabilities, reward function, and actions. So in reinforcement learning problems, if we have the transition probabilities between different states with different actions, we deal with model-based techniques like policy evaluation and value iteration. But if we don't have these probabilities, we deal with model-free reinforcement learning techniques. In model-based reinforcement learning techniques, we deal with a Bellman equation. You can see these two equations in this page. There are two functions that are common in two equations: function pi and function p. Function pi is our policy, and function p is the transition probabilities for different between different states with different actions. And there is a common component in these two equations, that are in bracket. You can see this bracket called Bellman backup. There are two components in this bracket. First part is R, which is our rewards, and another part is the next value or equality. Policy iteration comprises of two stages. At the first stage, we have policy evaluation, in which we define a for loop to find optimal values for each state. At first, we choose the action A with the policy, and then according to the Bellman equation, we calculate the values of each state, and if the changes between the updated values and previous values is lower than a threshold, we will break. And at the second stage, we have policy improvement, in which we will um, calculate the Q values with Bellman equation, and then we will find the optimal policy. I'm going to talk about a Monte Carlo method, which is a model-free reinforcement learning technique. In this technique, at first we define a generate function to generate our episodes, and it is similar to other reinforcement learning techniques in this part. This part is similar to other reinforcement learning techniques. At first, we reset the environment, and then we define a for loop for completing the episode, and then we take an action with our policy, which is epsilon greedy in this in Monte Carlo, and then we take a step in our environment, and we receive, and we save all results. Okay. Let's go to the algorithm of Monte Carlo, the foundation of the algorithm, because those things that I said is about generate function, which is similar to other reinforcement learning techniques. But I'm going to talk about the foundation of Monte Carlo method. Uh, in model-based techniques, I mean policy iteration and value iteration, we had transition probabilities between different states with different actions. So according to these transition probabilities, we could determine the optimal policy. But in model free techniques like Monte Carlo, we don't have the dynamic of system, and we don't have the transition probabilities. So in Monte Carlo, we finished at first we finished each episode. I mean, we finished each episode, and we received those results that I mentioned in generate episode function, and after that, according to these rewards, we could update our policy. I mean that after finishing each episode, we could update the policy. So At first, we should generate an episode, and when we generate an episode and the episode complete, then we could update our policies. So in Monte Carlo, we just update each state and action once in whole the episode, and we never update each state and action uh, every step that we face this step and this action. So we update just once in a whole episode. So we define an if conditional command uh, for this purpose, and then we should consider that we should assign the we should assign all rewards that we received from that state and that action to the end of the episode, to each state and action. I mean that you can see command R is equal to sum reward bracket T and to the end of the episode. So we assign the all rewards that we receive from that state and action to the end of the episode. And we can update the values and our policy with these rewards, and we will update our policy. In Monte Carlo, to estimate optimal answer, random sampling is used, and but there is a big problem regarding Monte Carlo, because in this strategy, because this strategy update values at the end of the episode, which can be inappropriate for the vast majority of tasks, especially in control engineering, because in control engineering we usually use online algorithms. So TD learning is beneficial for these purposes. You can see the main formula of TD learning. VS equal to VS plus alpha times R plus gamma VS prime minus VS. To use, I bring an example to show you how we can use this formula for updating values. You can see for update state 1 1, we use okay, the current value is 0.9, so we put this value instead of VS. And in other part of formula we have alpha, so this book puts 0.1 instead of alpha, and this is constant, and then we have R, I mean a reward, but you should know we just have non-zero values for reward at the last state. So in this step we have 0 for reward, and this book puts 1 instead of gamma, and then we have VS second, which is 0.6 in this example, and the current value of Vs is 0.9. So the next value of this state is 0.87. So you can see how we can use TD learning for updating the values. SARSA and Q-learning are other model-free reinforcement learning techniques. These two techniques use the TD learning formula that is introduced in previous page, but there is a difference between these two techniques because SARSA because SARSA use epsilon greedy for both taking an action and updating the policy, but in Q-learning, which is named off policy algorithm, we use epsilon greedy for adopting an action, but for updating the policy, we use the best choice for the next action. So this Q-learning is known as off policy algorithm.